Close your eyes and imagine the most inhospitable place you can think of on Earth, perhaps the scorching heart of the Sahara Desert, or the frozen darkness of Antarctica in winter, or the crushing depths of the ocean's deepest trenches. These places challenge human survival, pushing the limits of what our species can endure. Yet, compared to many worlds beyond our solar system, Earth's most extreme environments are oases of hospitality. Tonight, we embark on a peaceful journey to the most terrifying planets in the known universe, worlds so hostile, so extreme, so utterly alien that they challenge our very conception of what a planet can be. These are places where the laws of physics create conditions beyond nightmare, where the familiar rules of temperature, pressure, and chemistry twist into configurations that seem impossible, yet are startlingly real. We've discovered thousands of exoplanets orbiting distant stars, and among them are worlds that defy imagination. There are planets where glass rains sideways in supersonic winds, worlds where the surface is an ocean of molten lava, glowing red-hot beneath carbon clouds, planets so dark they absorb nearly all light that touches them, appearing as voids against the cosmos, places where iron vaporizes in the atmosphere and condenses as metallic rain. As we drift through this narrative, let yourself contemplate these extreme worlds from the safety of your mind, from the comfort of Earth's gentle embrace. There's something strangely calming about exploring cosmic terrors from a distance, about understanding that the universe contains such extremes while we float peacefully on our temperate blue world. They show us how fortunate we are to inhabit a world in the narrow band of cosmic possibility where life can flourish. They demonstrate that Earth, with its moderate temperatures, breathable atmosphere, and liquid water, is extraordinary, not typical, but rare and precious. The planets we'll explore tonight exist at the edges of planetary possibility, too hot or too cold, too massive or too small, too close to their stars or too far, orbiting stars too violent or already dead. Each represents a different failure of habitability, a different way the universe creates worlds hostile to life as we know it. Yet these worlds are not evil or malevolent. They simply exist, following the laws of physics and chemistry under conditions vastly different from Earth's. Their extremes arise naturally from their formation and evolution, from the cosmic accidents of mass, composition, orbital distance, and stellar environment that shaped them. So settle in, take a deep breath, and prepare to tour the universe's most terrifying worlds. Let the cosmic horror inspire not fear but wonder, not anxiety but appreciation for the remarkable planet we call home. These distant hells make our Earth seem even more like heaven. Our journey begins with planets subjected to temperatures so extreme that matter itself transforms into alien states we rarely encounter on Earth. These are the hot Jupiters and ultra-hot Jupiter's gas giants orbiting so close to their parent stars that they're roasted to impossible temperatures. Consider HD 189733b, a planet orbiting a star about 64 light-years from Earth. At first glance, this world might seem beautiful, its cobalt blue, resembling Earth when viewed from space. But this resemblance is hideously deceptive. The blue color doesn't come from water oceans, but from silicate particles in the atmosphere that scatter blue light, the same particles that fall as molten glass rain. The temperature on HD 189733b exceeds 1000 degrees Celsius, 1832 degrees Fahrenheit, hot enough to melt silver. But temperature is just the beginning of this world's horrors. The planet orbits its star once every 2.2 days, locked in such a tight embrace that tidal forces create winds exceeding 8,700 kilometers per hour, over 5,400 miles per hour, 7 times the speed of sound. These are the fastest winds ever detected on any planet. Now imagine that these supersonic winds carry not water droplets, but molten silicate glass, essentially tiny droplets of liquid quartz. As these particles are hurled horizontally across the planet at impossible speeds, they would shred anything in their path. Standing on HD 189733b, if you could somehow survive, the heat and pressure would mean facing a horizontal sandblasting by molten glass moving faster than bullets, all beneath skies of deceptive blue. WASP-12b presents a different infernal scenario. This planet orbits so close to its yellow dwarf star, completing an orbit in just 26 hours, that it's being literally consumed by stellar gravity. The planet is egg-shaped, stretched by tidal forces into an elongated ellipsoid. The side facing the star reaches temperatures around 2,500 degrees Celsius, 4,532 degrees Fahrenheit, hot enough that the atmosphere is steadily being stripped away and devoured by the star. Observations suggest WASP-12b will be completely consumed within about 10 million years, a blink of an eye in cosmic time. The planet is spiraling inward, its death foretold by gravitational mathematics. Any observer on this world would witness a sun filling half the sky, its surface detailed and violent, while feeling the planet literally falling apart, its atmosphere bleeding into space in a long tail of escaping gas. Kelt 9b holds the record as the hottest known exoplanet. Orbiting a massive blue star, this world reaches daytime temperatures around 4,300 degrees Celsius, 7,800 degrees Fahrenheit, hotter than some small stars, hot enough to vaporize most metals. At these temperatures, molecules cannot survive. The atmosphere contains atomic hydrogen, iron, and even heavy elements like magnesium and chromium in gaseous form. The planet's night side is somewhat cooler, only about 2,000 degrees Celsius, but still hot enough to melt most rocks. This temperature difference drives ferocious winds that attempt to redistribute heat around the planet. Kelt 9b is so hot that it's likely losing mass, with its atmosphere evaporating into space at a tremendous rate. The planet may eventually evaporate entirely, leaving behind only a bare core. Kepler 10b offers yet another vision of hell. This rocky planet orbits so close to its star, much closer than Mercury to our Sun, that its daytime temperature reaches about 1,400 degrees Celsius, 2,500 degrees Fahrenheit. The surface is likely an ocean of molten lava, glowing red and orange like a heated crucible. Rocky material that would be solid and stable on Earth exists here in liquid form, flowing in lava currents driven by tidal forces and temperature differences. The planet completes an orbit in just 20 hours. Days and years are nearly the same, passing in less than an Earth day. The star hangs huge in the sky, an overwhelming disk of fusion fire. The night side might cool enough for some materials to solidify into temporary crust, only to be melted again as rotation carries them back toward the star-facing hemisphere. This is a world in constant geological chaos, a surface that never achieves stability. Corot 7b, another scorched rocky world, presents an even more bizarre scenario. With daytime temperatures around 2,500 degrees Celsius, the planet is hot enough that rocks vaporize. The atmosphere likely contains gaseous rock, silicon, oxygen, magnesium, iron in vapor form. When these vapors rise high enough to cool, they condense not into water or ice, but into tiny rock droplets that fall as rocky rain. Imagine standing impossibly on Corot 7b's surface. Above you, clouds of vaporized stone would condense into pebbles of rock that rain down, only to vaporize again when they hit the searingly hot surface. Pools of molten rock would lie everywhere, fed by this strange hydrological cycle of stone rather than water. The distinction between solid, liquid, and gas, normally clear for rocks, blurs into a nightmarish continuum. These ultra-hot worlds challenge our understanding of what a planet can be. They represent extreme failure modes of planetary habitability, places where temperature alone makes life impossible, where the environment is so hostile that even sophisticated technology would struggle to survive for moments. Yet these worlds exist in abundance across the galaxy, reminding us that Earth's moderate warmth is an extraordinary gift, a cosmic rarity we should never take for granted. Moving beyond temperature extremes, we encounter planets where pressure, gravity, or exotic chemistry creates conditions equally terrifying, but in fundamentally different ways. These are worlds where the familiar behavior of matter breaks down, where substances adopt forms unknown on Earth. Gliese 436b presents one of the most perplexing scenarios in exoplanet science. This Neptune-sized world, about 33 light-years away, has surface temperatures around 440 degrees Celsius, 822 degrees Fahrenheit, hot enough to vaporize water. Yet models suggest the planet is largely composed of water, which should boil away at such temperatures. How can this be? The answer lies in pressure. The immense gravitational pressure deep within Gliese 436b compresses water into exotic forms of ice that remain solid even at temperatures of several hundred degrees Celsius. These aren't the familiar ice we know, they're bizarre high-pressure ices with crystalline structures impossible under Earth conditions, forms called Ice 7 and Ice X. Imagine descending into Gliese 436b. You'd pass through a hot atmosphere of hydrogen and helium. Deeper, you'd encounter a layer of supercritical water, neither liquid nor gas, but a strange hybrid state. Deeper still, despite temperatures that would boil water at the surface, you'd find solid ice, compressed by the weight of the layers above into a crystalline form denser than liquid water, a form that can exist at hundreds of degrees. This planet is, impossibly, a ball of burning ice. 55 Cancri E offers a different kind of material horror. This super-Earth, about twice Earth's diameter and 8 times its mass, orbits its star so closely that its year lasts just 18 hours. With surface temperatures around 2,400 degrees Celsius, the planet is a hellscape of molten rock. But what makes this world particularly terrifying is its composition. Models suggest 55 Cancri E's interior may be rich in carbon rather than oxygen-rich silicates. Under the immense pressures inside the planet, this carbon may have crystallized into diamond. The planet's core might be an enormous diamond larger than Earth itself, wrapped in layers of graphite and carbides, all covered by a surface ocean of molten silicon carbides. Picture this: a world where the ground beneath your feet, if you could stand on it, is liquid carbide floating atop layers of graphite, which in turn encase a diamond bigger than any world we've ever known. The very rocks are fundamentally different from Earth's, built from carbon chemistry rather than silicon-oxygen chemistry. It's a planet that's literally precious and absolutely lethal. WASP 7-6b, orbiting a star 640 light-years away, demonstrates another exotic phenomenon. The planet is tidally locked, always showing the same face to its star, much like the Moon to Earth. The permanent day side reaches about 2,400 degrees Celsius, 4,300 degrees Fahrenheit, while the permanent night side is somewhat cooler at about 1,500 degrees Celsius. This temperature difference drives ferocious winds that carry atmospheric material from day to night. On the day side, iron vaporizes into the atmosphere as gaseous atoms. These iron atoms are swept by winds to the night side, where temperatures are cool enough barely for iron to condense back into liquid droplets. Rain on WASP 7-6b consists not of water, but of molten iron, falling from dark clouds in a metallic drizzle. Standing on the night side, you'd witness iron rain falling from above, each droplet glowing orange with residual heat splattering when it hits the surface. The day side would see iron evaporate constantly from the ground, rising as vapor to feed the night's rain. This world has a metal cycle analogous to Earth's water cycle, but horrifyingly alien in its specifics. TRES 2b, about 750 light-years distant, is the darkest known planet. It reflects less than 1% of the light that hits it, making it darker than coal or black acrylic paint. Despite orbiting very close to its star and having temperatures around 1,800 degrees Celsius, the planet appears as a nearly perfect black orb, a void against the cosmos. Why is TRES 2b so dark? The likely answer lies in exotic atmospheric chemistry. At such high temperatures, molecules like titanium oxide and vaporized sodium absorb light across many wavelengths. The planet's atmosphere is essentially a light trap, grabbing photons and converting their energy into heat rather than reflecting them back to space. Looking at TRES 2b from nearby would be like staring into an abyss, a spherical shadow against the stars, perhaps faintly glowing with its own infrared radiation, but otherwise seeming to be made of darkness itself. These worlds of extreme pressure and exotic chemistry reveal how matter behaves under conditions rare or absent on Earth. They are laboratories of impossible materials, burning ice, solid diamond cores, iron rain, light-absorbing atmospheres that create voids in space. Each represents a different branch of planetary possibility, a different way that physics and chemistry can create worlds utterly incompatible with human experience. Before we explore planets in lethal orbits, let us visit some of the strangest and most alien worlds yet discovered planets whose very existence challenges our understanding of what a world can be. WASP 121b, nicknamed Hot Saturn, orbits so close to its star that it's being stretched into an egg shape by tidal forces. The planet is so hot, around 2,500 degrees Celsius on the day side, that water molecules in its atmosphere are being torn apart by stellar radiation. Heavy metals like magnesium and iron escape the planet's gravity as vapor, while compounds like titanium oxide, which exists as white paint pigment on Earth, exists as gas in this world's stratosphere. What makes WASP 121b particularly strange is that it may be raining liquid gemstones. The extreme temperatures and pressures in the upper atmosphere could allow clouds of corundum, sapphire, and ruby and perovskite to condense and fall as precipitation. Imagine looking up and seeing dark clouds approaching, then experiencing rain not of water but of molten gemstones, each droplet a tiny ruby or sapphire, glowing with heat as it falls. Kepler 7b is a planet as light as styrofoam. Its average density is about the same as the material used in coffee cups. This Saturn-sized world is one of the puffiest planets known, with an atmosphere that extends far into space. The planet's extreme low density suggests it's primarily hydrogen and helium, heated by its star, until it swells like a cosmic balloon. Despite its low density, Kepler 7b has distinctive cloud patterns visible from space. Bright reflective clouds on its western hemisphere create variations in the planet's brightness. These clouds might be made of silicate particles or other exotic materials. Standing on this world, if you could somehow find a solid surface, would feel like being inside a giant cloud, surrounded by haze in all directions, with only the enormous star visible through the murk. OGLE 2005b, LG390LB represents a completely different class of horror. This is a cold super-Earth, about 5.5 times Earth's mass, orbiting a dim red dwarf star at a distance that makes it one of the coldest exoplanets known. With surface temperatures around -220 degrees Celsius, -364 degrees Fahrenheit, this world is colder than Pluto. Any atmosphere it once had has long since frozen and fallen as snow, coating the surface in layers of frozen nitrogen, oxygen, and other volatiles. The star it orbits is so dim that even at the planet's distance, it would appear as merely the brightest star in the sky, not a proper sun. The world exists in perpetual frozen twilight, dark and cold, with temperatures approaching those of interstellar space. Nothing moves on this world, no weather, no geological activity, no sound. It's a frozen monument to what happens when a planet forms too far from its star or orbits a star too feeble to provide warmth. TOI 849b presents yet another mystery. This is a Neptune-sized planet with no atmosphere, just a bare, rocky, metallic core exposed to space. Something catastrophic must have happened to this world. Either its atmosphere was stripped away by stellar radiation, or it's the exposed core of a failed gas giant, or it collided with another planet and lost its outer layers. Whatever the cause, TOI 849b now orbits its star every 18 hours with a surface of bare rock and metal. No protective atmosphere, no clouds, no weather, just exposed planetary core material baking under intense stellar radiation. The surface temperature exceeds 1,500 degrees Celsius. This isn't a planet that failed to form an atmosphere. It's a planet that lost everything, leaving only its dense heart naked to the cosmos. LHS 3800 and 44b is a rocky world, slightly larger than Earth, orbiting a cool red dwarf star. But don't let the familiar size fool you. This planet is utterly alien. It has no atmosphere whatsoever, just bare rock exposed to space. The day side reaches temperatures around 530 degrees Celsius, while the night side plunges to extreme cold. With no atmosphere to redistribute heat, the temperature contrast is stark and permanent. Observations reveal that the surface is likely solid rock, perhaps basalt with no dust or regolith layer. The planet is tidally locked, so the same hemisphere always faces the star. The day side is an eternal furnace of baked rock glowing dull red. The night side is frozen darkness. Between them lies a narrow twilight zone where temperatures might allow ice to exist, constantly sublimating on the day side and freezing out on the night side in an endless cycle. These worlds gemstone rain, styrofoam planets, frozen super-Earths, atmosphereless cores, worlds of bare rock demonstrate that planetary diversity extends far beyond what we initially imagined. Each new discovery reveals new ways that mass, composition, orbital distance, and stellar properties can combine to create worlds utterly unlike Earth and unlike each other. Some of the universe's most terrifying planets achieve their extremity not through inherent properties, but through their relationships with their stars or other celestial bodies. These are worlds caught in lethal orbits, subjected to forces and radiation that make them fundamentally hostile to any conceivable form of life. PSRB 1257 plus 12 system hosts 3 known planets orbiting a pulsar, a rapidly spinning neutron star, the collapsed core of a star that exploded as a supernova. These were the first exoplanets ever discovered, found in 1992, and they orbit in one of the most hostile environments imaginable. A pulsar spins dozens or even hundreds of times per second, and its powerful magnetic field generates beams of radiation that sweep across space like a lighthouse. The planets orbiting PSRB, 1257 plus 12, are constantly bathed in intense radiation, X-rays, gamma rays, and high-energy particles that would sterilize any surface and destroy any complex molecules. Moreover, these planets likely formed from the debris of the supernova that created the pulsar, or from a companion star torn apart by the pulsar's gravity. They were born in violence and live in constant radiation bombardment. Standing on one of these worlds, if the radiation didn't kill you instantly, you'd see a small, dense neutron star spinning impossibly fast, with beams of deadly radiation sweeping past you multiple times per second like some cosmic weapon. HD 80606b suffers a different kind of orbital torment. This gas giant follows an extremely elliptical orbit, varying from about 0.03 to 0.88 AU, from its star closer than Mercury to farther than Venus. This means the planet experiences wild swings in stellar heating over the course of its 111-day orbit. At closest approach, the planet's temperature soars by about 700 degrees Celsius in just 6 hours as it whips around the star at tremendous speed. The atmosphere responds violently to this thermal shock, generating supersonic shock waves that circle the planet. Then, as the planet retreats to the outer part of its orbit, it cools dramatically, only to be flash heated again on the next passage. Imagine living through these cycles, if you could survive. Days of relative stability, then a sudden rush toward a looming star that grows larger and hotter by the hour. The temperature soars, the sky brightens to intolerable intensity, storms of unimaginable power tear across the atmosphere. Then the star begins to recede, shrinking, cooling, as the planet flings itself back into the outer darkness for another extended period before the cycle repeats. Some exoplanets orbit binary star systems, two stars orbiting each other. Depending on the configuration, this can create extremely complex stellar radiation patterns. A planet orbiting far from both stars, circumbinary orbit, experiences two suns in its sky. But the radiation environment can vary dramatically as the stars themselves orbit each other, sometimes aligning, sometimes at opposition. Even more extreme are planets that orbit just one star in a binary pair, with the second star nearby. The planet receives radiation from its own star plus reflected and direct light from the companion. Temperature, radiation intensity, and even gravitational forces vary on complex timescales as the stellar binary orbits. The sky is never stable, never predictable in any simple way. Then there are the rogue planets' worlds, ejected from their star systems entirely, wandering through interstellar space in eternal darkness. These planets, untethered to any sun, experience no day, no seasons, no variation except the slow cooling as they radiate away their internal heat. A rogue planet is the ultimate isolation, floating through the void between stars, illuminated only by faint starlight from distant suns. If it once had life, that life died when the planet was ejected, as temperatures plummeted to near absolute zero. Any ocean would freeze solid. Any atmosphere would condense and fall as frozen precipitation, coating the surface in layers of nitrogen, oxygen, or other frozen gases. The horror of a rogue planet is the horror of total abandonment. It's a world that once knew a sun, that once experienced warmth and light, now cast into perpetual frozen night. It drifts for millions or billions of years through the vast emptiness between stars, perhaps eventually captured by another stellar system, perhaps wandering forever in the galactic wilderness. Some planets experience extreme tidal forces that flex their interiors, generating tremendous heat through friction. Io, in our own solar system, experiences this on a smaller scale. Jupiter's gravity kneads the Moon's interior, creating volcanic activity that makes Io the most volcanically active body in the solar system. Extrapolate this to exoplanets with even stronger tidal forces, and you get worlds where the surface is in constant upheaval, where volcanoes erupt continuously, where the ground heaves and buckles as tidal forces literally tear the planet apart from inside. These worlds in lethal orbits remind us that habitability depends not just on a planet's properties, but on its cosmic context, where it orbits, and what else is nearby. A world that might otherwise be temperate and pleasant can be rendered utterly hostile by an eccentric orbit, a dead stellar companion, or ejection into interstellar space. The architecture of a solar system matters profoundly for the planets within it. Beyond heat, pressure, and orbital extremes lie planets whose atmospheres themselves are the primary source of terror compositions, so toxic, so corrosive, or so alien that they represent chemical hells incompatible with life as we know it. HD 209458b, known as Osiris, is a hot Jupiter whose atmosphere is being actively stripped away by stellar radiation. Spectroscopic observations have detected an enormous envelope of escaping hydrogen, helium, carbon, and oxygen atoms surrounding the planet, streaming away into space like a comet's tail millions of kilometers long. But it's not just the atmospheric escape that makes this world terrifying, it's what's in the atmosphere. Observations have detected sodium, carbon monoxide, carbon dioxide, methane, and water vapor, all at temperatures around 1000 degrees Celsius. This isn't a breathable atmosphere. It's a toxic soup of reactive chemicals at temperatures that would vaporize flesh instantly. The planet orbits its star once every 3.5 days at a distance where stellar radiation is about 100 times stronger than Earth receives. This radiation drives complex photochemistry, breaking apart molecules and creating free radicals and reactive species. The atmosphere is a constant chemical battle, with molecules being created and destroyed on short timescales, all at temperatures hot enough to glow. HATP-7b presents a different atmospheric nightmare. This hot Jupiter has winds of about 18,000 kilometers per hour, carrying clouds of corundum aluminum oxide, the same material that forms rubies and sapphires. But these aren't precious gemstones you'd want to collect. They're tiny particles suspended in an atmosphere of 2,200 degrees Celsius, whipped into supersonic winds that would sandblast anything in their path with hard mineral particles. The planet shows dramatic atmospheric changes, with observations suggesting that storms of corundum clouds move across the planet, temporarily changing its brightness. Imagine looking up and seeing clouds not of water vapor, but of vaporized gemstone material, dark and ominous, approaching with winds faster than any terrestrial hurricane, ready to scour the landscape with their abrasive cargo. Venus in our own solar system offers a nearby example of atmospheric horror. While not as extreme as some exoplanets, Venus's atmosphere is 96% carbon dioxide with clouds of sulfuric acid, surface pressure 92 times Earth's, and temperatures around 465 degrees Celsius, hot enough to melt lead. The atmosphere is so dense that it creates a greenhouse effect that makes Venus hotter than Mercury despite being farther from the Sun. Soviet Venera probes that landed on Venus in the 1970 seconds and 80 seconds survived only minutes before succumbing to the heat, pressure, and corrosive atmosphere. The images they transmitted showed a dim orange landscape of flat rocks under hazy skies, no blue, no water, no relief from the oppressive conditions. It's a vision of what could await on many exoplanets with thick CO2 atmospheres. Some theoretical models suggest planets could exist with atmospheres of molecular hydrogen under such extreme pressure that the hydrogen becomes metallic, a liquid metal atmosphere. These worlds would exist around the transition between gas giant and solid planets, with conditions so extreme that the familiar distinction between atmosphere and solid surface blurs. Standing on such a world, if you could, you'd be immersed in an ocean of metallic hydrogen, dense and conductive, possibly with a temperature of thousands of degrees. Light wouldn't penetrate far into this metallic fluid. Electrical currents would flow through the atmosphere itself, potentially generating magnetic fields of terrifying intensity. This isn't air or water, but something fundamentally different, a state of matter that exists only under conditions alien to Earth. GJ 1214b, a water world about 40 light-years away, might seem less terrifying than hellish lava planets. But consider its atmosphere, possibly a thick layer of water vapor, creating immense pressure and greenhouse heating. The atmosphere might be hundreds of kilometers thick, transitioning from supercritical steam near the surface, neither gas nor liquid, but a hybrid state, to cooler water vapor higher up. A traveler descending through GJ 1214b's atmosphere would pass through layers of increasingly dense steam, eventually reaching conditions where the distinction between atmosphere and ocean disappears. You'd be in supercritical water, unable to distinguish whether you're flying through dense vapor or swimming through thin liquid. Below this might lie a high-pressure water ocean kilometers deep, and only at the bottom would you finally encounter something solid. The concept of breathing would be meaningless on most exoplanets. Their atmospheres contain no oxygen, or contain oxygen bound up in toxic compounds like carbon monoxide. They might be too thin to sustain pressure, or so thick they'd crush a human instantly. They might be made of hydrogen and helium like Jupiter, or carbon dioxide like Venus, or exotic combinations of chemicals that exist only under extreme conditions. Even if temperature were somehow tolerable, Even if pressure were survivable, the chemistry of most exoplanet atmospheres would be rapidly lethal. They're not air but chemical reactors, photochemical laboratories, or high-pressure fluid systems completely incompatible with terrestrial biochemistry. HD 80606b suffers a different kind of orbital torment. This gas giant follows an extremely elliptical orbit, varying from about 0.03 to 0.88 AU from its star, closer than Mercury to farther than Venus. This means the planet experiences wild swings in stellar heating over the course of its 111-day orbit. At closest approach, the planet's temperature soars by about 700 degrees Celsius in just 6 hours as it whips around the star at tremendous speed. The atmosphere responds violently to this thermal shock, generating supersonic shock waves that circle the planet. Then, as the planet retreats to the outer part of its orbit, it cools dramatically, only to be flash-heated again on the next passage. Imagine living through these cycles if you could survive days of relative stability, then a sudden rush toward a looming star that grows larger and hotter by the hour. The temperature soars, the sky brightens to intolerable intensity, storms of unimaginable power tear across the atmosphere. Then the star begins to recede, shrinking, cooling, as the planet flings itself back into the outer darkness for another extended period before the cycle repeats. Some exoplanets orbit binary star systems, two stars orbiting each other. Depending on the configuration, this can create extremely complex stellar radiation patterns. A planet orbiting far from both stars, circumbinary orbit, experiences two suns in its sky. But the radiation environment can vary dramatically as the stars themselves orbit each other, sometimes aligning, sometimes at opposition. Even more extreme are planets that orbit just one star in a binary pair, with the second star nearby. The planet receives radiation from its own star plus reflected and direct light from the companion. Temperature, radiation intensity, and even gravitational forces vary on complex timescales as the stellar binary orbits. The sky is never stable, never predictable in any simple way. Kepler 1.6b, made famous as a real-life Tatooine, orbits both stars of a binary system. The planet sees two suns in its sky, one larger and brighter, one smaller and dimmer. As the stars orbit each other, every 41 days, the planet's illumination varies in complex ways. During eclipses, when one star passes in front of the other from the planet's perspective, the sky briefly darkens. The planet experiences not one sunset but two, as each sun dips below the horizon at different times. While this might sound beautiful, and in some ways, it is the complexity creates challenges for any potential life. The irregular illumination patterns, the varying radiation environment, the complex gravitational interactions all make this a far more chaotic environment than Earth's stable single-sun system. K2-141b presents perhaps the most bizarre orbital horror yet discovered. This rocky planet is so close to its star that its orbit takes just 7 hours, and it's tidally locked with permanent day and night sides. But what makes this world truly terrifying is its proposed surface composition and dynamics. Models suggest the day side is a magma ocean liquid rock extending hundreds of kilometers deep, heated to over 3,000 degrees Celsius by stellar radiation. Rock vaporizes from this magma ocean, rising into the atmosphere as mineral vapor silicon monoxide, oxygen, sodium, and silicon dioxide. Supersonic winds carry these vapors to the night side, where temperatures drop enough for them to condense and fall as rock rain. The fallen rock flows back to the day side as magma rivers, completing a rock cycle analogous to Earth's water cycle, but operating at temperatures that would vaporize most spacecraft. The entire planet is essentially a heat engine, with energy from the star driving a continuous circulation of liquid and vaporized rock. GJ 367b adds another dimension to orbital horror. This planet is among the densest exoplanets known, likely composed mostly of iron, an enormous metallic ball orbiting a red dwarf star once every 8 hours. At this distance, the planet experiences extreme tidal forces that may have stripped away any lighter materials, leaving only the dense iron core. The surface temperature exceeds 1,500 degrees Celsius, hot enough that the iron surface may be partially molten, glowing red-orange like heated metal in a forge. The planet's density is nearly twice that of Earth, creating surface gravity about 1.5 times stronger despite the planet's smaller size. Standing on GJ 367b, if the heat didn't vaporize you instantly, would mean experiencing crushing gravity while standing on a surface of molten iron, beneath a sky filled by a looming red star. WASP 18b orbits so close to its star that tidal forces are predicted to cause the planet to spiral inward and be destroyed within less than 1 million years, perhaps much sooner. The planet completes an orbit every 23 hours, and each orbit brings it fractionally closer to its star. The tidal forces are so strong that they may be heating the planet's interior to extreme temperatures, possibly causing geological activity that would make Earth's most violent volcanic eruptions seem tame. The fate of WASP 18b is sealed. It will eventually be torn apart by tidal forces and stellar gravity, its material accreting onto the star or being flung into space. This is a world on death row, counting down its remaining orbits before execution by gravitational forces. CoRo T2b experiences another kind of stellar violence. Its host star is extremely active, producing frequent and powerful stellar flares, eruptions of magnetic energy that blast X-rays and charged particles into space. The planet, orbiting close to this violent star, is constantly bombarded by this radiation, which heats the atmosphere and may be slowly stripping it away. Living on CoRo T2b would mean enduring sudden increases in radiation as stellar flares erupt, each one potentially delivering doses of X-rays that would be lethal to any known form of life. The planet's atmosphere serves as a shield, but it's a degrading shield, slowly eroded by the relentless stellar assault. This is a world at war with its star, engaged in a battle it's slowly losing. Not all terrifying worlds announce their hostility with extreme heat or violent atmospheres. Some present more subtle horrors worlds where light itself behaves strangely, or where darkness is so complete that it creates its own category of terror. Tres 2b, mentioned earlier for its darkness, represents planets that don't merely lack their own light, but actively absorb almost all light that reaches them. Reflecting less than 1% of incident light, this world appears as a black sphere, a hole in space. Only a faint red glow from its extreme temperature betrays its presence. The psychological impact of such darkness would be profound. Evolution has equipped humans with strong aversion to absolute darkness. It triggers primal fears of predation and disorientation. A world that appears as a void, where you could see the stars beyond it but barely perceive the planet itself, touches something deep in our psychology. It's not just dark, it's antithetical to vision, to light itself. Tidally locked planets, worlds that always show the same face to their star, present a different illumination horror. On these worlds, one hemisphere experiences eternal day, the other eternal night, with only a narrow twilight band between them where the sun perpetually hovers at the horizon. The permanent night side of a tidally locked planet would be utterly dark, illuminated only by starlight and perhaps by airglow if the atmosphere is suitable. Temperatures would plummet far below those on the day side. If the planet has an atmosphere, winds would rage from the hot day side to the cold night side in a relentless attempt to redistribute heat. But the darkness would never lift. No dawn, no sunset, no cycles, just eternal night. Conversely, the day side would never experience darkness. The star would hang fixed in the sky, perhaps moving slightly due to orbital eccentricity, but never setting. Shadows would point in the same direction always. There would be no night to bring relief from the heat and light, no darkness to allow rest. The sun would be an eternal fixture, wearing at the psyche with its unchanging presence. Planets orbiting red dwarf stars, the most common type of star in the galaxy, face unique illumination challenges. Red dwarfs emit most of their light in the infrared, with relatively little visible light. A planet in the habitable zone of a red dwarf would be much closer to its star than Earth is to the Sun, and likely tidally locked. On such a world, daytime would be dimly red, with the star appearing much larger than the Sun, but giving off a deep crimson light. Colors would appear different. Blues and greens would be hard to see, everything tinted in shades of red and orange. Vision as we know it would function poorly in this light. The illumination would feel perpetually like dusk, never bright, never dark, just an endless red twilight. Brown dwarf planets, worlds orbiting failed stars that never achieved full stellar fusion, would experience even stranger illumination. Brown dwarfs emit most of their radiation in the infrared, invisible to human eyes. A planet orbiting a brown dwarf would experience daylight, that we couldn't see infrared radiation warming the planet, but providing no visible light. To human eyes, such a world would appear to be in darkness, illuminated only by starlight from distant true stars. Yet infrared cameras would reveal a large, warm object dominating the sky, a sun you can feel but not see. This inversion of our normal relationship with sunlight creates a profound sense of wrongness, a world heated by invisible fire. Some planets might orbit in extremely elliptical orbits, where the amount of light received varies enormously over the course of a year. A planet might spend most of its orbit in cold, dim conditions, with its sun appearing small and distant. Then, during a brief perihelion passage, the star would grow rapidly in size and brightness, flooding the planet with light and heat for a short period before retreating again. The psychological and biological adaptations required for such a world would be extreme. Life would need to endure long periods of darkness and cold, then sudden periods of intense radiation and heat. Any evolved vision would need to handle vastly different light levels. The world would feel unstable, unreliable, with the most important celestial object, the sun, behaving erratically. Rogue planets, wandering interstellar space, experience ultimate darkness. With no star, there is no day, only the faint illumination of distant stars and galaxies. Perhaps an occasional brief brightening if the planet passes near a star during its wandering. The planet might retain internal heat, possibly even generating a magnetic field and maintaining geological activity, but it would do so in perpetual darkness. The horror of such darkness is existential. Its darkness not as the absence of day, but as the permanent state of existence. Its isolation on a cosmic scale, a world cut off from the light and warmth that make most planets habitable, drifting alone through the void. For a conscious being on such a world, the sky would show distant galaxies and stars, beautiful but unreachable, emphasizing the terrible isolation. These worlds of aberrant light remind us that habitability requires not just the right temperature and chemistry, but also appropriate illumination. Light, its quantity, quality, stability, and cycle shapes the possibilities for life and for consciousness. Worlds with too much or too little light, or light of the wrong type, or light that behaves erratically, are fundamentally hostile to life as we understand it. What makes these planets terrifying isn't merely their physical extremes, it's how those extremes challenge our understanding of what a world can be, how they violate our expectations and create cognitive dissonance. Let us contemplate what these cosmic nightmares reveal about the universe and about ourselves. Human psychology evolved on Earth, shaped by Earth's specific conditions. We find comfort in moderate temperatures, in the cycle of day and night, in stable ground beneath our feet, in air we can breathe. Our nervous systems are calibrated to Earth's gravity, our eyes to its light levels, our skin to its temperature range. When we imagine these extreme exoplanets, we're forcing our Earth-adapted minds to confront conditions completely outside our evolutionary experience. The result is a particular kind of existential terror, not fear of a predator or a physical threat we might fight or flee, but horror at conditions so far beyond our reference frame that we can barely conceptualize surviving them. Consider the terror of glass rain on HD 189733b. We understand rain. It's familiar, often pleasant. We understand glass, fragile, transparent, useful. But glass rain moving at supersonic speeds inverts both concepts, creating something that uses familiar elements to construct utter alienness. Our minds struggle to integrate these concepts. Or consider burning ice on Gliese 436b. Ice means cold to us, it's definitional. Fire means hot. Burning ice is almost a contradiction in terms, yet physics allows water to be solid at hundreds of degrees under sufficient pressure. Our everyday intuition fails completely, leaving us disoriented, unable to rely on familiar concepts to navigate this world. The eternal day or eternal night of tidally locked planets creates a different psychological terror. Humans are deeply circadian creatures, shaped by the 24-hour rotation of Earth. Remove that cycle, impose eternal light or eternal darkness, and fundamental biological rhythms break down. Sleep becomes difficult, time perception distorts, psychological stability erodes. It's not immediately lethal, but it's profoundly disturbing. Scale also contributes to terror. When we contemplate a diamond larger than Earth at the core of 55 Cancri E, or a comet tail of escaping atmosphere millions of kilometers long streaming from HD 209458b, the sheer scale defeats comprehension. Our minds evolved to handle human-scale objects and distances. Planetary-scale phenomena are so far outside this range that they trigger a particular kind of terror, the terror of insignificance, of being utterly dwarfed by natural forces. There's also terror in the violence and instability of these worlds. Supersonic winds, temperature swings of hundreds of degrees in hours, surfaces of molten lava, iron rain, atmospheric collapse and resurrection. These worlds are not stable homes, but active zones of violence. They remind us how gentle Earth is, how stable, how uncommonly calm and nurturing our world is compared to the cosmic norm. Yet perhaps the deepest terror comes from realizing that these worlds are not rare exceptions but common outcomes. Most exoplanets we've found are not Earth-like. Hot Jupiters are abundant. Super-Earths orbiting close to their stars are common. Worlds in the habitable zone with Earth-like conditions are rare, perhaps vanishingly rare. This realization inverts our cosmic perspective. We might hope that Earth-like worlds are typical, that the universe is filled with green planets, with blue skies and pleasant temperatures. But observation suggests the opposite. Earth is the exception, the unusual outcome. Most planets are some version of hell, too hot or too cold, too massive or in the wrong orbit, with the wrong atmosphere or no atmosphere at all. This statistical truth carries its own existential weight. We live on one of the few worlds where consciousness can contemplate the universe, surrounded by countless worlds where consciousness cannot exist. We are cosmically isolated by physics and chemistry, living on an island of habitability in an ocean of hostile worlds. Yet there's something strangely comforting in cataloguing these horrors. By understanding what makes planets uninhabitable, we better understand what makes Earth special. Each discovery of a hellish exoplanet is also a celebration of Earth's habitability. Each world of glass rain or iron snow makes us appreciate gentle water falling from clouds. Each world of eternal day or night makes us grateful for Earth's rotation. These terrifying worlds are teachers. They expand our understanding of planetary possibilities. They demonstrate the range of conditions physics and chemistry permit. They challenge our assumptions and force us to think beyond Earth's narrow band of comfort. They prepare us, perhaps, for what we might encounter when humanity finally ventures to other star systems. As you contemplate these worlds, let the terror transform into wonder. Yes, these places are hostile beyond imagination. Yes, they violate our intuitions and challenge our understanding. But they exist. They are real. They are part of our universe. The cosmos is not obligated to be comfortable or comprehensible, it simply is. Our privilege is to observe it, to study it, and to marvel at its terrible diversity. Having toured the most terrifying planets in the known universe, we must confront an intriguing question. Could life exist even in these extreme conditions? Not life as we know it, not comfortable and familiar, but life nonetheless hardy, adapted, thriving in environments that seem impossible. Scientists distinguish between planets that are uninhabitable for humans and planets that are uninhabitable for any conceivable form of life. These are not the same thing. The conditions that would kill a human in seconds, extreme heat, crushing pressure, toxic atmospheres, might be comfortable or even necessary for exotic biochemistries we've barely imagined. Consider extremophiles on Earth organisms that thrive in conditions we consider extreme. Thermophiles live in boiling water at hydrothermal vents. Acidophiles flourish in solutions with pH lower than battery acid. Halophiles grow in salt concentrations that would desiccate most life. Psychrophiles function at temperatures well below freezing. Barophiles thrive under pressures that would crush human bones. These Earth extremophiles prove that life's tolerances extend far beyond human comfort zones. They suggest that on exoplanets with conditions extreme by our standards but stable on their own terms, life might adapt and flourish. The hot Jupiters and tidally locked worlds we've described might not host life, but worlds somewhat less extreme might. The permanent night side of a tidally locked planet, for instance, would be hostile by human standards, dark, cold, possibly swept by fierce winds. But it might have liquid water if greenhouse gases trap enough heat. It might have chemical energy from volcanism or tidal heating. These ingredients, liquid water, energy, stable conditions over time, are the basic requirements for life as we understand it. Life on the night side would need to derive energy from chemistry rather than photosynthesis, as organisms do at Earth's deep-sea vents. It would need to tolerate darkness, cold, and possibly high winds. But these adaptations are not impossible, they're just different from the solar-powered, temperate biochemistry familiar on Earth's surface. Even on worlds with corrosive atmospheres or extreme temperatures, life might find niches. Planets with thick atmospheres might have altitude zones where conditions are milder. Tidally locked worlds might have habitable twilight bands between eternal day and eternal night. Planets orbiting red dwarfs, despite their dim light, receive sufficient radiation in the habitable zone for liquid water and possibly photosynthesis adapted to infrared light. Some scientists have speculated about life forms radically different from Earth's, based on different solvents or biochemistries. Where Earth life uses water as a solvent, life on Titan might use liquid methane. Where Earth life uses carbon-oxygen chemistry, life on other worlds might use silicon-based or nitrogen-based chemistry. Where Earth life requires moderate temperatures, life elsewhere might operate at extremes we find lethal. These speculations remain hypothetical. We have no evidence of such exotic biochemistries. But the universe is vast and diverse, and it seems presumptuous to assume that only Earth-specific biochemistry can generate life. The terrifying planets we've explored might be stepping stones in our understanding, extremes that help us define the boundaries of habitability and perhaps discover forms of life beyond those boundaries. Even on planets too extreme for life on their surfaces, subsurface habitats might exist. A world with a molten lava surface might have habitable zones beneath the crust, where liquid water exists under pressure, insulated from the hellish surface above. A frozen rogue planet might maintain liquid water oceans beneath kilometers of ice, warmed by radioactive decay or tidal heating, hosting life in perpetual darkness. The discovery of even simple life bacteria-equivalent organisms on any exoplanet would revolutionize our understanding. It would prove that life is not unique to Earth, that it arises wherever conditions permit. If we found life on a world we considered marginal or extreme, it would expand our definition of habitability and increase our estimates of life-bearing worlds in the galaxy. Conversely, if we thoroughly explore marginally habitable worlds and find them lifeless, it would suggest that life is rare, that the gap between chemically possible and biologically realized is wide. This would be significant too. It would teach us that life requires more than just the right chemistry, that some additional factor or series of factors is necessary. The terrifying planets we've described are unlikely to host life. They're too extreme, too unstable, too hostile, even for the most optimistic extrapolations of extremophile adaptations. But they define the boundaries of planetary possibility, and those boundaries contain a middle range where life might persist. By understanding the extremes, we better understand the margins of habitability. As astrobiology progresses, as our telescopes improve and our understanding deepens, we may discover life in unexpected places. We may find that planets we dismissed as too hostile actually harbor organisms in protected niches, or we may find that even relatively mild planets remain sterile, that life is profoundly rare. Either discovery would reshape our cosmic perspective. As our journey through the universe's most terrifying planets draws to a gentle close, let us reflect on what these extreme worlds teach us about the cosmos and about our own remarkable planet. The exoplanets we've explored tonight are real. They're not science fiction or nightmare inventions, but actual worlds orbiting actual stars, places where physics and chemistry create conditions beyond our everyday experience. HD 189733b really does have glass rain and supersonic winds. Kelt 9b really is hotter than many stars. Gliese 436b really has burning ice. These aren't metaphors, they're descriptions of physical reality. This reality check is simultaneously humbling and empowering. Humbling because it reveals how narrow our band of experience is, how much of the universe operates under conditions we cannot survive. Empowering because we can understand these places despite never visiting them, because human intellect can comprehend conditions utterly alien to human experience. The diversity of planetary conditions across the universe is staggering. Each exoplanet we discover seems to push the boundaries of what we thought possible. Each new observation reveals planetary behaviors, compositions, or environments we hadn't predicted. The universe is more creative, more varied, more extreme than our imaginations anticipated. This diversity arises from the physics of planetary formation and evolution. Planets form from the disks of gas and dust around young stars. Their composition depends on where in that disk they form close to the star where it's hot and only rocky materials can condense, or far from the star where ices can freeze. Their subsequent evolution depends on their mass, orbital distance, stellar type, and countless other factors. The result is a vast parameter space of planetary possibilities. Change any variable mass, distance, composition, stellar radiation, and you get a different outcome. Earth occupies one tiny region of this parameter space, the region where temperatures allow liquid water, where the atmosphere is breathable, where conditions remain stable enough for life to emerge and evolve over billions of years. Most parameter space produces planets hostile to life as we know it. Too close to the star yields molten hellscapes like Kepler 10b. Too far yields frozen wastelands or gas giants. Too massive yields crushing gravity and thick atmospheres. Too small yields airless rocks that can't retain atmosphere. Most combinations of variables produce uninhabitable worlds. Yet Earth exists. Despite the long odds, despite occupying such a narrow region of planetary parameter space, our world achieved the specific combination of properties that permits not just habitability, but the emergence of complex life and eventually consciousness. This is simultaneously extraordinary and perhaps inevitable given enough planets. Even rare outcomes must occasionally occur. The terrifying planets help us appreciate Earth's gentleness. After contemplating supersonic glass rain, Earth's gentle water rain seems like a blessing. After imagining eternal day or eternal night, Earth's 24-hour rotation seems perfectly balanced. After considering atmospheres of vaporized rock or metallic hydrogen, Earth's nitrogen-oxygen mix seems not just breathable but precious. Every exoplanet discovery is an implicit celebration of Earth. Each new hellworld reminds us what we have, what we could so easily not have had. The glass rain worlds and lava planets and burning ice worlds make Earth seem not ordinary but extraordinary, not typical but rare and wonderful. There's also beauty in these extreme worlds, beauty in their terrible extremes. The cobalt blue of HD 189733b is beautiful even as its winds and heat are deadly. The darkness of Tres 2b has an aesthetic power, a black world against the stars. The diamond core of 55 Cancri E, though inaccessible and surrounded by horror, represents material wonder. These worlds inspire not just fear, but awe. Perhaps this is the deepest lesson of planetary terror. that the universe contains extremes we can barely imagine, yet we can understand them, appreciate them, and learn from them. We don't need to find these worlds comfortable to find them valuable. Their alienness is precisely what makes them important. They expand our understanding, challenge our assumptions, and reveal the universe's creativity. As you drift towards sleep, let your mind wander among these extreme worlds. Imagine the cobalt skies of HD 189733b, the eternal night of tidally locked planets. The diamond heart of 55 Cancri E. Imagine worlds beyond these, worlds yet to be discovered, planets even more extreme, even more alien, even more terrifying and wonderful. But then return to Earth, return home. Feel the gentle gravity holding you to the ground, not crushing but comforting. Feel air moving across your skin, air you can breathe, air at a temperature that doesn't burn or freeze. Know that above you, day will turn to night in familiar rhythm, that water rain will fall gently from clouds, that the ground beneath you is stable rock, not molten lava or burning ice. We are travelers on a rare world, witnessing a universe mostly hostile to our form of life, but spectacular in its diversity. The terrifying planets are out there, hot Jupiters and dark worlds, glass rain and iron snow, diamonds and darkness, and endless extremes. But we are here, on Earth, able to contemplate them from comfort and safety. The cosmos is vast and mostly terrible, but it has produced here and there worlds like Earth, where life can flourish and consciousness can emerge to observe and wonder. We are privileged to live in such a time, on such a world, with the knowledge and technology to discover and understand the universe's terrible diversity. Rest well, cosmic explorer. Dream of worlds beyond imagination, of extremes beyond experience, of the universe's endless creativity in crafting hostile wonders. But wake grateful that you wake here, on Earth, on this gentle island in the cosmic ocean of extremes. May your appreciation of Earth's kindness deepen with every exoplanet discovery, with every journey through cosmic terror to cosmic wonder. The terrifying planets await our continued study. They have secrets yet to reveal, lessons yet to teach. But tonight, as you rest, know that the most important lesson they offer is this: Earth is precious, Earth is rare, Earth is home, and that is no small thing in a universe of glass rain and burning ice.